So the environmental aspect, okay? And basically in chapter 4, we cover all the subtopic and also a sub aspect that actually we can try to consider, okay, for all the potential chemical reaction and pathway before we finalize and select the final best chemical reaction. This is basically what we discussed in our chapter 4. So basically our chapter 3 and chapter 4, they all are mainly cover the theory part, okay? They try to explain, okay, what are the subtopic and also why we need to consider this subtopic in order to assist us to consider before we make the final decision and selection. So basically this is what we learned in chapter 3 and chapter 4. Okay. Okay. So now, okay, so we proceed to our chapter 5. Okay. Okay. So now for our today lecture, we will proceed with to our chapter 5. Okay. Heat integration. Okay, so if let's say you still remember, okay, uh, so once we already select, okay, select the best chemical reaction pathway, what we are going to do is we will try to either apply the onion models or maybe the synthesis step that proposed by Mr. Power in order to complete, okay, the process flow diagram based on the selected chemical reaction and also the selected reaction pathway. Okay, once we already have the finalized process flow diagram PFD, okay, what we can do is we can proceed to the process integration or task integration. So process integration or task integration, that means we will try to link all the selected processes and also the equipment that involve in the selected reaction pathway or involved in the process flow diagram to link together, okay, to combine together by using the process stream. And also under the task integration or process integration, we will also try to perform the pinch analysis in order to develop the heat exchanger network. So remember, we can only perform the pinch analysis to develop the heat exchanger network after we already finalize the process flow diagram. So meaning that pinch analysis and also the development or design of the heat exchanger network can only be carried out or conducted once we already finalize our process flow diagram. Okay? But of course, before you can perform the pinch analysis, so you have to know how to actually how to extract the relevant data from the finalized process flow diagram in order that okay you have the sufficient information to allow us to carry out the pinch analysis. Okay, so remember normally we will try to carry out the pinch analysis under the task integration or process integrations once we already have the final process flow diagram. Okay, so once we already carry out the pinch analysis, design or already develop the heat exchanger network, then we will proceed to try to install the heat exchanger in the process flow diagram in order to recover, okay, or reduce the heat energy that released in our chemical plant in order to minimize or lower down the fresh, okay, utility that actually we need to supply to our chemical plant in order to reduce the what we call the OPEX, okay, of our chemical plant. So, and these are the subtopic that actually we are going to cover in our today lecture 5 and chapter 5. Okay, so before we proceed, before I teach you how to apply the pinch analysis, how to design and develop the heat exchanger network, okay, I think it's good if let's say I can try to explain and recap, okay, what is heat exchanger? Okay, so now you try to imagine now in your chemical plant, you have a hot stream. Let's say the hot stream here, the temperature is 90 degrees Celsius. You want to reduce the temperature to become, let's say, 60 degrees Celsius. And also at the same time, you also have a cold stream. The cold stream, the initial temperature is at 40 degrees Celsius, but you want to heat up the temperature of the cold stream here to become 75 degrees Celsius, let's say. Okay, so you consider the hot stream here. The stream here is known as a hot stream. Why? Because the initial temperature is higher. Okay, it's hot, and now we want to bring down the temperature. So that's why you call it hot stream. If let's say you want to reduce the temperature of the hot stream here, what you need to do is you need to try to remove out the heat energy from the hot stream here. Am I right? In order to bring down its temperature. At the same time here, the process stream is known as a cold stream. Why? Because the initial temperature is lower, and now we want to try to bring out the temperature to become 75 degrees Celsius. So that's why the stream here is known as a cold stream. So common sense, if let's say you want to increase the temperature from 40 to 75 degrees Celsius, of course you need to supply the heat energy to the cold stream here in order to bring out its temperature. Okay? And okay, initially, okay, in our finalized process flow diagram, what we will do is, if let's say you want to bring down the temperature of the hot stream here, what you will do is you will try to install a cooler in order to cool down the temperature of the hot stream here to achieve the target that you want to achieve. And for the cold stream, in the finalized process flow diagram, you will include the heater. This one is the symbol of heater. In order to supply extra energy to the cold stream here to increase its temperature from 40 to become 75 degrees Celsius. This is actually what we do and what we install in our finalized process flow diagram. And of course, if let's say you already install a heater, you install a cooler to bring down temperature, of course you need to supply the cooling water to the cooler here in order to bring down its temperature. And the cooling water here is considered as part of our utility. And also for the cold stream, you install a heater, then of course you need to supply either the hot water or hot stream in order to bring out the temperature of the process stream here. And the hot water or the hot steam that you are going to transfer and supply to the heater here, so you will also contribute to the cost of the utility, which is part of our OPEX. Okay, so what we can do is actually the hot stream here we want to remove out the heat energy. Why not when we try to remove out the heat energy from the hot stream here, we try to transfer the heat energy that release out from the hot stream here and recycle and supply to our cold stream. So in that case, we can reduce the fresh energy that we are going to supply to our process flow diagram or our chemical plant. So meaning that we will try to capture and reuse the energy that release out from the hot stream here and reuse to heat up to bring out the temperature of the cold stream here. So this is what we call heat recovery, so that we can try to reduce the fresh utility, either the amount of the fresh hot water, hot steam, or the cooling water that actually we need to supply to our chemical plant. So the benefit is, first, we can reduce the cost of our utility. And the second, we can also make our chemical plant become more eco-friendly. This is the reason, why we need to install a heat exchanger. So by installing the heat exchanger in our chemical plant, it allows us to try to recover, to reuse the heat energy that released out by the hot stream, supplied to the cold stream here. And the heat transfer is actually will take place inside the equipment we call heat exchanger. So inside the heat exchanger, normally we have a hot fluid and also the cold fluid. So imagine our hot fluid here that we want to bring down in temperature, is transferred into a heat exchanger. And at the same time, another cold stream that we want to bring out in temperature is supplied, okay, also transferred into the heat exchanger. So inside the heat exchanger here, the heat energy will transfer from the hot fluid stream into the cold fluid stream in order to achieve our target to recover the heat energy to reduce the utility of our chemical plant. Okay, so that's why, okay, in the process industry, okay, normally the transfer of the heat energy, okay, between two different process streams is carried out in a heat exchanger. And normally it involves a hot fluid and also the cold fluid. Even though the hot fluid and cold fluid, they will be transferred into the heat exchanger, okay? But the heat transfer process actually can be carried out without mixing the hot and cold fluid, okay, together, okay? Why? Because later the hot fluid, okay, will flow into the shell of the heat exchanger, okay, let's say. And also the cold fluid will transfer, okay, inside the tube, okay, that installed inside the heat exchanger in order to allow the heat recovery process to be carried out without mixing them together, okay? So that's why, okay, the hot and cold fluid do not come into direct contact with each other. They are separated by the shell and also the tube that can be found inside the heat exchanger, okay? And the heat transfer, okay, involved in the heat exchanger here, involve the convection and also the conduction. Let's say here is your heat exchanger. Okay, now inside the heat exchanger, we have a lot of different tubes. Let's say the cold stream is transferred into the tubes, and the hot fluid is flow through the cell outside the tube here. And what will happen is the heat energy will be transferred out, okay, due to the temperature gradient that can be found, okay, in the heat exchanger. Temperature gradient, that means temperature difference, okay. The temperature difference is mainly due to the temperature between the hot stream and also the cold stream. So remember, according to thermodynamics, heat energy always transfer from the hot region or hot fluid into the cold fluid. So this is the theory that actually allow us to try to recover the heat energy, okay, by using the heat exchanger, okay, by applying the law of thermodynamics. Okay, so when the heat energy is transferred out, okay, from the hot stream, first you will be transferred from the hot stream liquid into the tube here, tube surface. Tube is actually solid, okay. It is fabricated by using, let's say, okay, some of the metal, for example, stainless steel and so on. So the heat energy that involves transfer from the liquid, okay, fluid, okay, to the solid tube here, okay, the heat transfer is transferred through convection, okay. And also, okay, normally when we design the heat exchanger, we need to determine what is the thickness of the tube that you are going to install and use in the heat exchanger. Once the heat energy is transferred out from the hot fluid, it will be transferred to the outer surface of the tube. And then the heat energy will transfer from the outer surface to the inner surface before it absorbed by the cold fluid flowing inside the tube side. So the heat transfer, okay, within the tube thickness here, okay, the heat is transferred through conduction. Once the heat energy reach the inner surface of the tube side, then only the heat energy is transferred into the cold stream here to increase its temperature. And the heat energy transfer from the inner surface solid to the liquid here, let's say, the heat energy is transferred through convection. And basically this is the two heat transfer mechanism that involve in the heat exchanger. Okay, so far any question before I proceed to introduce the type of heat exchanger that we normally use in chemical plant? So Edmund, so far do you have any question regarding to the mechanism, the working principle of heat exchanger? Edmund missing in action. No, okay, thank you. Okay, thank you. Okay, thanks for your feedback, Alvin. Okay, Edmund, where are you? Edmund missing in action or you don't want to reply me, eh?
No question, sir.
Okay, thank you, thank you. Okay, so if let's say you have any question, let me know, Edmund. Okay, so now, just now I explained how the heat exchanger is actually allow us to try to recover the heat energy in order to reduce the fresh utility that we need to supply to our chemical plant. And basically, these are the 4 different types of heat exchanger that we normally encounter and use in the chemical industry or industry. The first one we call the double pipe heat exchanger. The second one we call shell and tube heat exchanger. The third one we call plate heat exchanger. This one is normally used in the food and beverage industry. And the last one is a cross flow heat exchanger. This one is normally we use to try to increase or reduce the temperature of gas stream. Then normally we will prefer the cross flow heat exchanger. Okay, so we go to the first, heat exchanger. We call it double pipe heat exchanger. Okay, so the first one is the double pipe heat exchanger. This one is actually considered the most common heat exchanger among all the 4 heat exchanger that I show you just now here. Okay, so normally, if let's say the flow rate of the process stream is low or small, then normally we will select this type of this type of heat exchanger. Okay, so means that normally the double pipe heat exchanger will only be installed if let's say the flow rate of the process stream that we are going to handle is low or small, then we will prefer this simple heat exchanger. You see this one is the example, the picture of the double pipe heat exchanger that we normally use in the industry. Okay, and normally first we have a tube here, and normally the cold fluid or cold process stream will flow through inside the tube here, and the tube here later it will be surrounded or covered by another what we call the shell, and the hot fluid will flow through inside the shell. Since the shell here will cover the outer surface of the tube here, so later the heat energy will be transferred from the hot fluid into the cold fluid in order to bring down the temperature of the cold fluid and at the same time reduce the temperature of our hot fluid. This is how the double pipe heat exchanger allow the heat to be transferred from the hot fluid into the cold fluid. Okay. Okay, so far any question? Okay, so depends on the direction of the flow of the cold fluid and also the hot fluid. The heat exchanger here, can be designed either in co-current or counter-current flow. So if let's say the cool stream and also the hot stream, they are flowing in the similar direction, then in that case it's considered as a co-current flow heat exchanger. But if let's say the cold stream and also the hot stream, they are actually flowing in opposite direction, then in this case the heat exchanger is said to be designed or operated in counter current flow. And normally in heat exchanger we prefer counter current flow. Why? Because based on the scientific what we call the experiment that already conducted and proven by the scientists and engineer. Normally if let's say the heat exchanger, if let's say they are actually operated or designed under the counter current flow, normally the efficiency, the heat transfer is actually higher compared to the heat exchanger operated under the co-current flow. Meaning that the what we call the performance of counter current flow is actually already been proven by the scientific evidence. So that's why normally when we design or select the flow for our heat exchanger, we prefer counter current flow. Okay, so this one is the simplest type of heat exchanger that we can install in industry. Okay, but if let's say the flow rate of the process stream that we are going to handle is actually big or large, then in that case, we might need to install a shell and tube heat exchanger. This is actually how the shell and tube heat exchanger look like. Okay, so similar inside the shell and tube heat exchanger, there are actually a lot of tube. Okay, they are actually installed or constructed. Okay, and arranged in bundle. Okay, inside the heat exchanger, and later the parallel tubes here will be covered or surrounded by the shell, this one, okay, shell. And what will happen is, okay, if let's say now the hot fluid is flowing inside the tube side, then later the cold fluid will be transferred into the heat exchanger here through the what we call the entrance, okay, of the shell side of the heat exchanger. So what will happen is, okay, when the hot fluid flow through the tube inside the heat exchanger, the heat energy will be transferred out from the hot fluid and transfer into a cold fluid later in order to bring up the temperature of the cold fluid to increase its temperature. And at the same time, once the heat energy is transferred out, it can also reduce the temperature of our hot fluid in order to reduce its temperature. This is how the shell and tube heat exchanger, okay, to transfer the heat energy out from the hot fluid in order to bring up the temperature of cold fluid. Okay, okay. This one is okay. This heat exchanger is very common. Normally, we are used in chemical industry. Okay. So beside that, okay, before we proceed, okay, this one is also considered as a shell and tube heat exchanger. You see, inside the heat exchanger, actually there are a lot of tube. Okay, they are actually arranged, okay, in parallel, arranged in bundle, okay, and parallel, okay, each other, and installed inside the shell in order to allow the heat energy to be transferred out from the hot fluid, okay, into the cold fluid. Okay, but of course, okay, the number of the tube that you are going to install in the heat exchanger, okay, you'll need to consider lah. Okay, what is the final temperature you want to achieve, and also what is the flow rate and amount of the process stream that you are going to handle. All these parameters, they will actually directly determine the number of the tube that you are going to design and include in the heat exchanger, and also including the wall thickness and so on. Okay, so meaning that, okay, the design of the heat exchanger, okay, you'll need to consider, okay, the final temperature you want to achieve, and also the amount of the fluid that you are going to handle by the heat exchanger here. Okay, but of course there are a lot of factors you need to consider before you finalize and design the suitable heat exchanger for your chemical plant. Okay. Okay, beside that, okay, this one is another type of heat exchanger that we normally can be used in the industry. This one we call plate heat exchanger. Okay, but plate heat exchanger normally, okay, is used in the food and beverage industry. Okay, okay, and normally compared to the other types of heat exchanger, plate heat exchanger, okay, normally, okay, it's heat transfer coefficient is higher compared to the other types of heat exchanger. So meaning that if let's say the heat transfer coefficient of plate heat exchanger is higher, meaning that later, okay, this heat exchanger, it can actually transfer the heat energy more efficiently compared to the other types of heat exchanger. Why? Due to the high heat transfer coefficient. So even though its heat transfer coefficient is good, it can transfer the heat energy efficiently compared to the other types of heat exchanger, but there is a limitation. Okay, so the limitation is this. Okay, this type of heat exchanger, plate heat exchanger, is only suitable to be utilized. Okay, if let's say the operating pressure or the pressure of the process stream that you are going to handle is lower than 30 bar. If let's say the pressure or operating pressure is more than 30 bar, then this type of heat exchanger is not suitable. Even though its heat transfer coefficient is high, it can transfer the heat energy efficiently, but is limited by its operating pressure. Beside that, this one we call cross flow heat exchanger. And normally this type of heat exchanger is used to bring out or bring down the temperature of air or gas or gaseous mixture. This is actually how the inner surface, the component that can be found inside the cross flow heat exchanger. Inside the cross flow heat exchanger, we have a lot of tube. So if let's say now we want to reduce the temperature of our air stream here. Then what we can do is, we can try to transfer the cold fluid to allow them to flow through the tube sides, tube side, inside the tube, and at the same time, the gas stream will flow through into the cross flow heat exchanger here, from this direction, you see, from this direction. But the cold fluid will flow through the tube from this direction. That means the flow of the gas stream and also the flow of the cold fluid now will form a perpendicular angle. Here is the direction of flow of our air. You see, but the cold stream flow in this direction, then you will form a perpendicular angle here. Right angle. They flow perpendicular. So in this case, this is how the cross flow heat exchanger transfer the heat energy from the hot air or hot gas into the cold stream in order to bring down its temperature. This is how the cross flow heat exchanger to recover and reuse the heat energy in order to minimize the fresh utility that we are going to use. So these are the 4 common heat exchangers that we normally encounter and use in the industry. So far, any question before we proceed? So Kumar, do you have any question before we proceed? Kumar, where are you? Where are you? Kumar?
Hi.
Hi, how are you?
I'm fine. How are you?
Fine. Good. Thank you.
Okay, bye.
So now, before I proceed. So far I already introduced the 4, the common heat exchanger that we normally install and encounter in the industry. Among these among these heat exchanger, right? The shell tube heat exchanger is the most common heat exchanger that we normally use in the chemical industry. So that's why if let's say you refer to your e-learning the website My Times, actually I also uploaded another what we call the information we call equipment sizing for heat exchanger. So inside the learning material here, actually I try to include the step and also the method how we can actually design a shell and tube heat exchanger. And inside the learning material here, they try to show you all the equation and also the information that we might need to apply in case we need to design a heat exchanger. This one the design of the shell and tube heat exchanger. Okay, this one, the learning material here, I already uploaded, okay, to your e-learning website, okay, my times. Okay, later you can download, okay, from your e-learning platform, e-learning website, in case in future you want to design a shell and tube heat exchanger. Okay, so make sure you download this learning material and keep a copy in your computer. Why? Because later in your final year, you might need, okay, you might need to design a heat exchanger, okay, in case, okay, you are expected to do so, okay. In case you want to design a heat exchanger, especially a cell and tube heat exchanger, then you may refer to the learning material that I provided to you here. Okay, this one is considered as a self-learning material. Okay, meaning that I'm not going to guide you step by step, okay, what are the equations you are going to use, but I just provide you the learning material here. So in case in future you need to design a shell and tube heat exchanger, then you can refer to the learning material here. And for your information, for the design of the shell and tube heat exchanger is not covered in our test or final exam. So meaning that the design of the heat exchanger will not be covered, okay, in our test and final exam. But of course, you need to download a copy and save a copy in your computer. Okay, in case in future you need to design a shell and tube heat exchanger, then you can refer the slide here as the learning material. Do you get what I mean? Okay, so remember the design of heat exchanger, the design of the tube and shell heat exchanger is not covered in our test and final exam. Okay, okay, so now we proceed. Okay, so just now I already introduced to you the common types of heat exchanger that we normally encounter and use in the industry. Okay, so as I told you just now, okay, so once we already finalize the process flow diagram PFD, then under the task integration or process integration, then we will start to try to determine the number and select the type of heat exchanger that we are going to use, okay, to include in our process flow diagram. But of course, okay, before we try to determine the number of the heat exchanger that we need to install in our process flow diagram, what we need to do is we need to develop or design a heat exchanger network first. And then based on the heat exchanger network, then only we know what is the number of the heat exchanger that actually we want to include in our process flow diagram. Okay? So in order to allow us to try to develop and design a heat exchanger network, the method or the analysis process that we are going to carry out is known as a pinch analysis. Okay? So remember, as I told you, so in the finalized process flow diagram that you develop based on the best reaction pathway that you selected, in the process flow diagram, if let's say you want to increase the temperature of a process stream, then you will install a heater. If let's say you want to reduce the temperature of the process stream, then you will install a cooler. So when you carry out the pinch analysis, you will develop and design a heat exchanger network. And based on the heat exchanger network, you will determine what is the number of the heat exchanger that you are going to include in the finalized process flow diagram here. By including the heat exchanger in the process flow diagram here, later actually you can try to reduce the number of heater and also the cooler that actually can be found in the process flow diagram in order to reduce the fresh utility, in order to reduce the cost of the utility that you are going to supply to your chemical plant. Why? Because later the heat energy can be recovered and recycled by replacing the heater and cooler here by using the heat exchanger. So meaning that, okay, we can only include the heat exchanger in our process flow diagram after we already finalize the process flow diagram and after we already come up with a heat exchanger network design. Okay, then only we can further proceed to include a heat exchanger in our process flow diagram. Okay. Okay, so I give you an example. Okay, let's say this one is your finalized process flow diagram. You see, wow. Okay, in your process flow diagram, you see so many cooler and heater. This one is heater. This one is cooler. And some more. This one is condenser. Okay, condenser. That means you are going to release or remove the heat energy out from the process stream lah, to condense the gas to become liquid. You see so many cooler and heater. So in this case, okay, for all the cooler and heater, you need to supply the fresh, okay, cooling water or the fresh hot water or hot steam in order to make sure the cooler and heater here can carry out, okay, their function or process properly. But you see, once we already, okay, carry out the pinch analysis, we already develop and design a heat exchanger network. What we can do is actually we can try to reduce the number of the heater and cooler that can be found in the process flow diagram here. You see, once you perform the pinch analysis, you see, now we can eliminate the cooler. We try to install a heat exchanger here, and the heat exchanger here will actually try to make use or recover or reuse the heat energy from the hot fluid stream here in order to transfer it into the process stream here to heat out the process stream here. So in that case, we can actually reuse and recover the heat energy to reduce the cooler and heater that require, and also reduce the number of the cooler and heater, and also reduce the amount of the fresh utility that you are going to supply to your process flow diagram. Okay. Then of course, okay, the number of the cooler and also heater here can also be, okay, reduced, okay, by replacing them by using the heat exchanger. But depends on your process flow diagram. Okay, sometimes in your process flow diagram, okay, you can only include one heat exchanger. But in some of your process flow diagram, okay, you can install 2, 3, or more than 3 different heat exchanger in order to recover and reuse the heat energy that involved in the process flow diagram. Depends on your process flow diagram. Okay, you will come up with different pinch analysis, and you will determine the number of the heat exchanger you can install. Okay. Okay, so far any question? So at this stage, okay, sorry, at this stage, at least you know what are the common type of heat exchanger that normally we can install in the chemical industry. Okay, what is the working principle of heat exchanger, and how we can actually try to reduce the cooler and heater by using the heat exchanger. So far, any question before we proceed? Okay. Okay, I assume there is no question, then we proceed. Okay, so look at here. Oh, sorry. Okay, so now we proceed. Okay, you see, assume this one is your process flow diagram. Before you carry out the pinch analysis to design the heat exchanger network to determine the number of heat exchanger, what you need to do is you need to know how to extract the relevant data from your process flow diagram before you carry out the pinch analysis. Okay, first, what you need to do is you need to draw a table. Okay, the first column here you need to put in stream number. So we need to write down to identify how many process streams that actually involved in our pinch analysis. Okay, so After that, the second column here, you need to write down the stream type. The stream type is either a hot stream or cold stream. Okay, I give you an example. We use the process flow diagram here as an example. Okay, you see, okay, we start with this one. You see, here is the process stream. Okay, inside the process stream here, it involves cooling process. How do I know the process here involves cooling process? We install a cooler here to bring down its temperature from 180 to become 80 degrees Celsius. So that means it involves cooling process lah. Even though the process stream here involves cooling process, but the initial temperature is higher. So that means before the cooling process is a hot stream. So that's why for this process stream is given the number stream number 1. And the process stream here is considered as a hot stream. So that's why I put hot here. Initial temperature, or we call start temperature, 180 degrees Celsius. What is the final temperature you want to achieve? 80 degrees Celsius. Here, 80 degrees Celsius. Here is our start temperature. Here is our target temperature we want to achieve. So this one is our stream number 1. So far, any question? So, okay, Alvin, I just use the process flow diagram here to try to explain how we are going to extract and get the relevant data from the process flow diagram to construct the table here before we proceed to pinch analysis. Okay, just now I didn't draw anything. I just use my mouse to show you how to get the data to put into the table here. Okay. Okay. So now we proceed. Okay. So, okay. So in the last column here, we need to put in the heat capacity flow rate. The heat capacity flow rate, normally we use CP to represent. So meaning that the CP is actually the short form. We indicate or represent the heat capacity flow rate of the process stream here. Okay, so normally in test, in final exam, normally the heat capacity flow rate, okay, they will directly provide to you. But if let's say in assignment, you want to do the pinch analysis, the heat capacity flow rate is not provided because it's an assignment. Okay, you need to know, you must know how you have to know how to calculate the heat capacity flow rate yourself. Okay, let me repeat. So normally in most of the cases in test or final exam, if let's say you want to carry out a pinch analysis, normally the heat capacity flow rate CP will be provided. Okay, but if let's say now, okay, later you want to solve the assignment, or maybe in your final year, you need to try to carry out a pinch analysis for your chemical plant design. And how you are going to determine the heat capacity flow rate? Okay, you need to try to, okay, get the heat capacity flow rate, calculate the heat capacity flow rate based on the properties that you have, okay, in the process stream here. Okay, how to calculate the heat capacity flow rate? You need to use the heat capacity, specific heat capacity of the process stream, multiply, okay, with their mass flow rate. Then you will get their heat capacity flow rate. Okay, so I repeat again. So if let's say in test and final, in most of the cases, the CP heat capacity flow rate will be provided. But if let's say they are not provided, okay, let's say in assignment they are not provided, then you need to identify the heat capacity flow rate of the process stream here yourself. How to calculate? By using the specific heat capacity multiply with their mass flow rate. Then you will get their heat capacity flow rate. And remember, the unit of the heat capacity flow rate is a kilowatt per degree Celsius. Okay, this is how we get the CP. Similar, you see, for stream number 2, okay, let's say, okay, okay, this one. No, sorry, this one. Okay, this one is considered our stream number 2, and we need to include in our pinch analysis. How do I know? Because the process stream here involve, okay, a cooling process. Why? Because we install a cooler here. So that means the initial temperature is higher, 130 degrees Celsius. So this one is a hot stream, stream number 2. Start temperature 130. Target temperature 40. How to get the heat capacity flow rate? Provided 40. If not provided, you need to use the specific heat capacity of the process stream here, multiply with its mass flow rate. Then you will get the CP here. Okay? So, okay, another example. This one. Okay, now I want to consider this process stream here. Why? Because it involves heating process. Even though it involves heating process, but the initial temperature of the process stream here is lower, 60. We want to bring out the temperature to the target temperature, 100 degrees Celsius. So that's why the process stream here, because the initial temperature is lower, so this one is considered as a cold stream. So that's why I put the cold stream here. Heat capacity flow rate provided. If not provided, we use its specific heat capacity of the process stream here, multiply with its mass flow rate. Then we will get the heat capacity flow rate here. This is how we extract the information of all the relevant process stream and put it in the table before we proceed to carry out the pinch analysis. Okay, remember, if let's say the process stream involve, okay, cooling process or heating process, then compulsory. Okay, you need to consider them in the table here before we proceed to the pinch analysis. And remember, for the stream type here, you make sure you put the correct answer in the column here. If let's say you assign the wrong stream type to the process stream here, then later, I'm sure later you have problem with your pinch analysis. Later, all your calculation will GG. Why? Because all your pinch analysis, all the calculation, they are actually carried out based on all the data that we included in the table here. So that's why you see, just now, okay, I spent a lot of time to explain to you how to extract the data from a process flow diagram, how to fill out the table here by using the correct information. Okay, so far, any question before we proceed to calculate the pinch analysis, to carry out the pinch analysis? This one very important, because if let's say you cannot extract the data correctly, I'm sure later you cannot determine the correct number of heat exchanger. Okay, thanks, Alvi. Okay, give me 30 seconds. Okay. Okay, done. Okay, we proceed. Okay, once we already come up with this table, right? First, we need to determine the minimum temperature. Later, all of our pinch analysis will be calculated and determined, okay, carried out based on the minimum temperature here. The temperature normally, okay, in test or in final, they will, okay, the minimum temperature will be provided. But if let's say in your design, okay, you might need to identify the minimum temperature, the suitable minimum temperature that you are going to use for your pinch analysis. Depends on the
Everybody got 36, bro.
Okay, it depends on the process that you are going to handle in your chemical plant. Okay, different process, okay, or different technology, they might need different temperature, minimum temperature difference to allow you to carry out the pinch analysis to try to get the most accurate number of heat exchanger. Okay, so this is the second step. Okay, determine the suitable minimum temperature difference. Okay, once we have the minimum temperature, then only we will proceed okay, to construct, okay, the temperature, the interval temperature diagram. Okay, once we already identify the most suitable minimum temperature difference, then we proceed to prepare the internal temperature diagram. Then we proceed to prepare the cascade diagram. And based on the cascade diagram, we will determine the pinch and also the minimum hot utility that we can achieve in our chemical plant, and also the minimum cold utility that actually we can achieve in our chemical plant. Okay, this is the procedure SOP, how we carry out the pinch analysis. Okay, and for the rest, the other point here, later I will directly explain by using the example later. Okay, but at least you know this is the flow, how to carry out the pinch analysis. Okay, so now look at here. Once we already identify the most suitable minimum temperature difference, we need to process to calculate the interval temperature for our hot stream and also the interval temperature of our cold stream. The equation here are fixed. So means that we always use the start temperature, the actual temperature that we use, that we already put in the table here in order to calculate the interval temperature. Okay, how to calculate the interval temperature? Okay, let's say we want to calculate the interval temperature of hot stream. We use the start temperature or actual temperature minus the minimum temperature difference divided by 2. For cold stream, we want to determine its interval temperature. We use its start temperature plus minimum temperature difference divided by 2. So be careful with the symbol here. For hot stream, we want to calculate the interval temperature. Here is minus. For cold stream, we want to determine the interval temperature. Here is positive. Why? Because hot stream. Why is hot stream? Hot stream, that means the initial temperature of the stream is higher. And we want to reduce its temperature. So that's why here we put negative to reduce its temperature. For cold stream, its initial temperature is lower. We want to heat up the temperature of the cold stream. So that's why we put plus to increase its temperature. This is how I memorize the equation here for the pinch analysis. So make sure you use the correct symbol to calculate the interval temperature. Okay? Okay, so I show you the example how to calculate the interval temperature. Okay, now we proceed. Okay, so now, okay, I will directly to explain how we can try to determine the interval temperature by using the example here. Okay, you see, now we have one example here. Okay, first I need to construct a table. How to construct a table? Similar to what I teach you just now. First, okay, identify the stream number and also the stream type. Okay, and also identify the start temperature. This one is the start temperature. This one is the target temperature. Okay, how we extract the data from the process flow diagram? Similar to what I teach you just now. Okay, okay, after that, what you need to do is you also need to determine the CP, okay, of all the process stream that involved in the pinch analysis here. Either the CP is directly provided in the question or you need to calculate yourself. If let's say you want to calculate yourself, remember what you need to do is you need to calculate the specific heat capacity of the process stream, multiply with its mass flow rate, then you will get the CP here. If let's say the CP is not provided. Okay? After that, you need to identify the most suitable minimum temperature difference. Okay? different processes, they have different, okay, suitable minimum temperature difference for the pinch analysis. Okay, so in this case, it is directly given 10 degrees Celsius. So that's why we can directly to apply 10 degrees Celsius. Okay, so now, first, we want to determine the interval temperature. Remember, you want to determine the interval temperature. Here are the equations. Hot stream, negative. Cold stream, positive. Look at here. I'm not going to repeat due to the time limitation. And I can tell you this one is very, very important as a chemical engineer. Okay, interval temperature. Add in another column. Write interval temperature. Look at here. Stream number 1. Hot stream. Hot stream, that means I will try to minus. How to minus? Use the start temperature. What is my start temperature? 180. Minus minimum temperature difference divided by 2. 10 divided by 2, 5. 180 minus 5, 175. Similar, okay, this one is my target temperature, right? Okay, how to calculate the interval temperature? Similar. 60 minus 10 divided by 2. That means 60 minus 5, 55. Okay? Okay, so similar. Stream number 2. Hot stream. 150 minus 10 divided by 2, 145. 30 minus 10 divided by 2, 25. This is how we determine the interval temperature for hot stream. How about cold stream? Similar. 20 start temperature, but cold stream, positive. 20 plus 10 divided by 2, 5, 25. 135 plus 10 divided by 2, 140. This is how we calculate the interval temperature for cold stream and hot stream. So far, any question? No question, Okay, so this is how we calculate the interval temperature by using the equation here. Remember, hot stream always is negative. Cold stream is positive. Okay? So in the lecture note here, in the example here, you see some of the interval temperature I put bracket. Okay, actually the bracket here can be ignored. Okay, the bracket here, you can actually ignore lah. You just put in the correct number is actually sufficient already. Okay, so the bracket can be ignored. Okay. Okay, so far any question before we proceed? Okay, first we extract the data from the process flow diagram. Second, we construct the table here. Third, we determine the most suitable minimum temperature difference. Fourth, we calculate the interval temperature based on the equations that I show you here. Okay, fifth, next step. We need to try to arrange the temperature. Start with the biggest temperature that can be found in the interval temperature here. So meaning that based on the calculate interval temperature here, which temperature is the biggest one? 175. So that's why now we try to arrange the temperature. We start with the biggest interval temperature, 175. What is the second biggest temperature after 175? What is the second? 145. 145. Third, 140. 140. Fourth, 85. 85. After 85, 25. 55. So 55. After 55, 25. Even though 25 appear 2 times in the interval temperature here, but we just write down once enough, 25. Okay, so meaning that after we already calculated the interval temperature, then we try to arrange temperature. Start from the biggest one, then the smallest one is away at the bottom part here. Okay, before we proceed to try to draw the interval temperature diagram. This is what we call interval temperature diagram. Okay, so why we need to arrange the sequence of the interval temperature, start from the biggest until the smallest? Because you see, for the interval temperature diagram here, the left hand side, the interval temperature, you see, make sure you put in the correct unit. The interval temperature, the sequence, how we are going to arrange them, is start from the biggest interval temperature. And the smallest interval temperature is always at the bottom part here. This is actually how we arrange the interval temperature in the interval temperature diagram here. How to arrange? Based on the sequence that I teach you just now. This one. You see? 175, 145, 140. 175, 145, 140. 85, 55, 25. This is how we arrange the interval temperature. Next, we draw horizontal line. You see the green color one, the blue color one. Draw horizontal line. Draw horizontal line. Draw the horizontal line, 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 and line. Okay, now we need to draw the diagram. So we need to refer back to our table here. We look at the interval temperature. For process stream number 1, the temperature is bring down from 175 to 55. So 175 is here. 55, our target is here. So we just draw a line down, start from 175 here down until it touch a 55 degrees Celsius here. Then this one label is stream number 1. Stream number 2. Stream number 2, 145 to 25. 145, start from here until 25. Label stream number 2. Stream number 3, we want to increase the temperature from 25 to 140. 25 here, then we go up until it achieve 140. Stream number 3. Similar method applied to draw the stream number 4 in the diagram here. And normally we will try to write down the CP also for each of the stream here. Stream number 1, what is the CP? 3. What is the CP for stream number 2? 1. Okay, normally we will try to label. Why? Because later we need to use the CP to construct the table here. So far, any question with the diagram here? Make sure you know how to draw the diagram up. If let's say you cannot draw the diagram, then later you have problem with the calculation. Okay, so now we proceed. Okay, now, after we draw the diagram here, we draw another table. First column is delta Tn, unit degree Celsius. How to calculate the delta Tn? Delta Tn is the difference between the temperature that can be found in the first horizontal line here with the second temperature that can be found in the second horizontal line here. What is the value here? 175. 175 minus 145, 145, 30 degrees Celsius. Then you put 30 degrees Celsius. Okay, second column here. How to determine the value here? Then you need to determine what is the difference between the temperature that can be found in the second horizontal line here and the third temperature that can be found in the third horizontal line here. 145 minus 140, 5 degrees Celsius. Similar 55, 140 minus 85, 55. 85 minus 55, 30. 55 minus 25, 30. This is how we determine the delta Tn here. Okay? Okay, so now we proceed. Okay, next, we need to proceed to the second column. how to calculate, how to get the value in the second column here. You need to apply the equation here. Okay, you need to apply the equation here. Okay, CP means the heat capacity flow rate. H means hot stream. C means cold stream. That means you need to add out all the heat capacity of the hot stream and then minus the total heat capacity of cold stream, then you will get the value here. Okay, I give you an example. For the first column here, the first column here, this one, you need to refer to the first gap here. What is the process stream that can be found in the first gap here? This one. Any other process stream can be found in the first gap here? No. So means that only process stream number 1 can be found in the first gap here. So some more, this one is hot stream. You see, initial temperature is higher, hot stream. So what is the CP of the hot stream here? 3. So that means this one is 3. Any cold stream can be found in the first gap here. Any cold stream cross the first gap here? No. So that means this one is 0. 3 minus 0, 3. This is how we get the value here. Okay, so I give you one more example. This one. Okay, this one is the second box. Then we look at the second gap here. Okay, similar. What are the hot stream that can be found in the second gap here? Stream number 1 and stream number 2, you see? Because hot stream 1 and hot stream 2, they cross the second gap here. So what is the CP of first and second process stream? 3, 1. 3 plus 1, 4. Minus, okay, what are the cold stream that can be found in the second gap here? Only this one. Only stream number 4, only cold stream number 4, okay, can be found in the second gap here. So what is the CP of stream number 4? 4.5. So 4 minus 4.5 minus 0.5. How to calculate the third box here? Similar. We look at the third gap here. Okay, what are the hot stream that can be found across the third gap here? Stream number 1, stream number 2. 3 plus 1, 3 plus 1, 4. Minus, what are the cold stream across the third gap here? Stream number 3, stream number 4. 2 plus 4.5, 6.5. Answer, minus 2.5. This is how we get the value here. Similar method applied to get the value here and the value here. So far, any question with the calculation here? Okay, now we proceed. Next, we need to calculate delta H. The delta H here means heat balance. Okay, the delta H here represent the heat balance that involved in the interval temperature diagram here. And the unit is normally kilowatts. Okay, if let's say the heat capacity CP that you are using, the unit is kilowatt per degree Celsius, then here is also kilowatts. First, how to calculate the heat balance? Very simple. You use the answer here, multiply with the delta Tn here. 3 multiplied with 30, 90 kilowatts. This is the energy that can be found in the first gap here. One more. How to get the value here? Negative 0.5 multiplied with 5, negative 2.5. This is the energy that can be found in the second gap here. How to get this one? 55 multiplied with 2.5. Then you will get the value here, negative 137.5. This is the energy can be found in the third gap here. Similar method apply in order to get the value here and the value here. This is how we determine the heat balance that involve in the gaps here. And the method how we determine the heat balance, I show you already how to get the heat balance here, right? The method is actually similar to the equation that's shown in the previous slide here. This one, you see? This one is heat balance. You need to determine the difference, okay, between the heat capacity of hot stream and cold stream, and then you use the answer, multiply with the delta Tn. Then you will get the heat balance. And the method I teach you how to get the answer here is actually similar to the equation that given in the previous slide. So far, any question? Okay, you see, I teach you step by step, you know. If let's say you refer to the e-book or reference book, they will just show you the diagram, show you the answer, and try to discuss the answer. Okay, but they won't try to show you step by step how to get the value here. So that's why our lecture today very, very important. So, okay, make sure you know how to construct the table. Okay, so this one we call interval temperature, okay, diagram. Okay, so next, we need to develop a cascade diagram. This one is what we call cascade diagram. Okay, look at here. I teach you how to draw the cascade diagram. Okay, just now we already arranged temperature here, right? Am I right? Okay, so in order to develop the cascade diagram here, similar, the interval temperature here, the sequence, we just follow and copy and paste, we put on the left hand side. You see, biggest interval temperature always at the top here. The lowest interval temperature always, okay, at the bottom side here. Okay, this is our left hand side of our cascade diagram. Okay, okay, next we draw horizontal line, horizontal line, horizontal line, horizontal line, horizontal line, horizontal line. Okay, so now here the box here we put hot utility. This one is fixed one. If let's say we want to construct a cascade diagram, here we always put hot utility. And the bottom here, the last box here, we always put cold utility. Okay? Okay, so next, we need to refer back to the heat balance. What is the heat balance? What is the first heat balance here? The first gap here, 90. Then here, the first gap here, we put 90. You see, 90. What is the heat balance in the second gap? Negative 2.5 kilowatts. So in the second gap here, we put negative 2.5. Negative 137.5. The gap here, third one, we put negative 137.5. This one, 60. Then here we put 60. Last one here, negative 30. Then the last gap here, we put negative 30. Then here is cold utility. Okay? Okay, so look at here. Next. Okay. Right hand side. This value, we always start with 0. So means that the value here is fixed one. We always start with 0. Okay? This one is fixed one. Don't ask me why is 0. Fixed one. Okay. 0 plus 90. You will get the answer here. 90 kilowatts. 90 plus negative 2.5. 87.5 kilowatts. 87.5 kilowatts plus minus 137.5. Negative 50 kilowatts. Negative 50 plus 60. Positive 10 kilowatts. 10 plus negative 30, negative 20 kilowatts here. This is how we get the value here, 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 here. So far, any question? No, okay. So look at here. The most important part. Okay. So look at here. Angelo want to show you something, Kuma. Okay, don't panic. Look at here. Open your eye. Open your eyes, Kuma. Okay, so look at here. This one is positive value. This one positive value. This one positive value. This one positive value. For the positive value, we ignore. We only look at the negative value. Okay, I repeat. Positive value, we ignore. We only compare and look at the negative value. You see, we have two negative value here. If let's say we only consider the numerical value of the negative number here, if let's say we only compare the numerical value of the negative value here, first one, second one, which one is actually bigger than numerical value? Can someone answer me? Because I want to make sure you all can follow me. First one, second one, which numerical value of the negative number here is biggest? Is the biggest, sorry. Okay, Shini is not here. Okay, which one is the biggest one? Okay, we only look at the value. We ignore the negative. We only compare the value among the negative answer, negative energy. But when we compare among them, we only look at the value. We ignore the negative. 50 and 20, which one is actually biggest? Yes, the first one, this one. Okay, we compare only the numerical value. The negative is just an indicator to show us which value we are going to compare them. Once we already identify the number that we are going to compare, then we will proceed to compare the numerical value without considering the negative. So that's why for these two negative value, 50, this one, the value is bigger. Why? Because 50 and 20, 50 is bigger than 20. So that's why later this one, 85 here, is considered as our pinch or pinch temperature. So if let's say in the question they ask you in test or final, they ask you to identify the pinch temperature, then your answer is 85 degrees Celsius. This is how we identify the pinch temperature. So far, any question before we move on and proceed? Okay, Shini is not here. Okay, so never mind, we proceed. Okay, done. Okay, we know this one is our pinch temperature. Okay, pinch temperature. Okay, so now what we can do is, okay, now we copy and paste the cascade diagram here. This one is the first cascade diagram we will prepare just now. So now we copy and paste, prepare another cascade diagram. Similar heat balance, similar interval temperature. But now we need to recalculate the energy here. Okay, okay, look at here. Okay, now look at. Okay, so this one I remove. Okay. Okay, so just now we already identified the pinch temperature. Why? Because among these two negative numbers, the value, numerical value here, 50, is larger than 20. So that's why I know this one, 85, is my pinch temperature. Okay? Okay, so now I want to convert the negative 50 here to become 0. So if let's say now I want to convert the negative 50 here to become 0, what I need to do is I need to add up the negative 50 here with positive 50. Why? Because when I add up the negative 50 with positive 50, then I can convert the value here to become 0 kilowatts. Am I right? So if let's say here I add up with positive 50, then what I need to do is the first value here 0, I also add up with positive 50. Then you see now the new value here is positive 50 kilowatts. So far, any question with the positive 50 here? So you have to know why I want to add up with positive 50. Why? Because this one is pinch temperature. Compulsory for cascade diagram, the method, once I already identify the pinch temperature, I must convert the value here to become 0. How I'm going to convert the negative 50 to become 0? I need to add up the value here, negative 50 with positive 50. Then I can convert the value to become 0. Negative 50 plus 50, 0. And then I proceed to add out the 0 with positive 50, 50 kilowatts here. Any question? Okay, no. Okay, look at here. Be careful. Okay, here is 50. Similar step, we proceed. 50 at 90, 140. 140 plus negative 2.5, 137.5. 137.5 minus 137.5, you will get a similar 0 here. Correct? Am I right? Okay. 0 plus 60, positive 60. Positive 60 plus negative 30, positive 30. This is how I get the new value here. And the first value at the top here, this one is known as minimum hot utility. Meaning that after I try to carry out the pinch analysis, after I try to install the heat exchanger, now I can further reduce the fresh hot utility in the chemical plant that I'm going to design. I try to reduce the fresh hot utility to become minimum value 50 kilowatts. Meaning that maybe before you carry out the pinch analysis, the fresh hot utility that you are going to supply to your chemical plant, let's say is 300 kilowatts. But after you try to carry out a pinch analysis, and after you installing the heat exchanger, you can try to reduce the fresh hot utility from the initial value 300 to become 50 kilowatts. This is what we call minimum hot utility. So meaning that if let's say you install the heat exchanger that calculated, okay, from the pinch analysis here, later you can reduce the hot utility from the initial value to the minimum value 50 kilowatts. This is the minimum. And also the last number here, this one we call minimum cold utility. So what is the meaning of minimum cold utility? Meaning that before you carry out a pinch analysis, maybe the energy, the cooling water that you need to supply to your plant is, let's say, 1000 kilowatts. But after installing the heat exchanger as suggested or recommended by the pinch analysis here, later you can reduce the fresh cold utility from the initial 1000 to the minimum value 30 kilowatts. So that you see, you can reduce a lot of fresh cold utility, so that you can make your chemical plant become more eco-friendly and also reduce the cost of the utility. This is what we call cascade diagram. Okay, so far, any question? No, Okay, no, good. Okay, we proceed to the last step. Okay, so next, okay, what we need to do is we need to we need to determine the pinch temperature for hot stream and pinch temperature for cold stream. How to calculate? Okay, here is the equation. Okay, here is the equation. How to calculate? Okay, very simple. Just now, what is your pinch temperature? 85. What is the minimum temperature you use just now? 10. So very simple. You use the pinch temperature that identified in the cascade diagram plus minimum temperature divided by 2, which is 5. Then this is the pinch temperature for hot stream. For pinch temperature for cold stream, similar. What is the pinch temperature that you identify from the cascade diagram? 85. But for cold stream, here we put negative. Minimum temperature 10 divided by 2, 5. 85 minus 5, this is the pinch temperature for cold stream. Remember, for pinch temperature for hot stream, here is positive. Pinch temperature for cold stream, here is negative. Okay? You see, pinch temperature, hot stream, positive. But just now, when we want to determine the interval temperature for hot stream, we positive. But now, with the Ballet inverse, become positive. And similar for the interval temperature for our cold stream just now, positive. And now with the Ballet inverse, become negative. This is how we determine the pinch temperature for hot stream and cold stream. Make sure you get the value here correct. If not, later you have problem with the design of heat exchanger network. So far, any question? No? Okay, we proceed. Okay, last step. Okay, so now last step, we want to develop a heat exchanger network. This is what we call heat exchanger network. Okay, I will show you how to develop the network here. Okay, first, okay, how many process stream involved in your example here? 4. 1, 2, 3, 4. Normally, the hot stream, we will put at the top here. Hot stream number 1, we draw from here to here. What is the initial temperature and also a target temperature? We need to refer to the table. Okay, be careful. We look at the actual temperature, 180 to 60. 180 to 60. What is the initial temperature of hot stream number 2? 150 to 30. 150 to 30. Okay, look at here. Cold stream, we need to increase the temperature from 20 to 135. 20 to 135. You see, now the flow of the hot stream and cold stream, they are actually different. Okay, counter current flow. Remember, okay, the highest temperature is always on our left hand side. The lowest temperature is always on our right hand side. Left hand side, high temperature. Okay, left hand side, high temperature. Left hand side, high temperature. Right hand side, low temperature. So cold stream, we want to increase its temperature. So that's why we flow from 20 to 135. So we put here. Hot stream, we want to cool down its temperature. So that's why we start from here, 180, flow to this direction to achieve the lower temperature. This is how we draw the line for the heat exchanger network. If possible, we try to include the CP for all the stream on the right hand side here. Why? Because later we need to do some calculation for our heat balance. Okay, so far any question? No. Okay, so proceed. We draw two vertical lines at the middle part of the heat exchanger network here. Here, 90 is our hot stream pinch temperature, 90. So we put 90. This one, 80, is the pinch temperature of our cold stream, 80. So we put 80. Remember 90 and 80 because 90 degree is higher. So that's why the higher temperature is always on our left hand side. The cooler, the lower temperature is on our right hand side here. 90, 80. Here is our pinch point. Here is considered as the region above the pinch point. Here is considered as the region below the pinch point. So far, any question? No, no, I proceed because I want to speed up because some of you have classes later. Okay, this one I explain later by using the example. Okay, so now look at here. I ask you how to draw the heat exchanger, how to determine the number of heat exchanger. Okay, so now, just now I said here is a pinch point. We always start with the left hand side, the region above the pinch point. So for the region above the pinch point, this is the guideline we need to always to consider. The CP of the hot stream must be always equal or lower than the specific, the heat capacity of the cold stream, 3 and 4 here. Okay, remember for left hand side, the region above the pinch point, this is the regulation we need to follow. The heat capacity of the hot stream must be lower or equal to the heat capacity of the cold stream. If let's say we want to try to transfer the heat energy. Okay, so look at here. Okay, look at here. Okay, just now this one is the pinch point of hot stream. This one is the pinch point of cold stream. This one very important. So if possible, you try to write down which one is hot, which one is cold. Okay, look at here. Okay, look at here. Okay, this one is our hot stream. I told you already, hot stream means we want to reduce the temperature from the higher temperature to a lower temperature. So that's why the heat energy must be transferred out from the hot stream and reused and supplied to the cold stream here, either this one or this one. So first, okay, you look at here. What is the initial start temperature? 180. Okay, look at here. This one is hot stream or cold stream? Hot stream. So that's why, because this one is hot stream, then we use the actual temperature 180 minus the temperature of the hot stream here. 180 minus 90, the balance is 90. 90 multiplied with 3, 270 kilowatts. This is your delta H, meaning that if let's say we reduce the temperature of the hot stream one here from 180 to become 90, the energy that actually we can separate out, recover, and reuse is 270 kilowatts. Okay? Okay, so now the hot stream must be paired with the cold stream, either stream number 3 or stream number 4. But when you pair up the hot stream here with the cold stream, you need to remember, you need to follow the rule that given here. The CP of the hot stream must be equal or lower than the CP of the cold stream. Okay, you see cold stream number 3, what is the CP? 2. This is the CP of your hot stream number 1, 3. Compared to 2, the CP of hot stream number 1 here is bigger or smaller than the CP of stream number 3 here? Bigger. But for this region, your CP of hot stream must be lower or equal. So meaning that I cannot pair up the hot stream number 1 with hot stream 3. Cannot. Why? Because it cannot meet the regulation here. So how about stream number 4? 4.5. This one, 3. Yes, I can pair up the hot stream number 1 with cold stream number 4 here. So what I can do is, okay, I draw a circle and also draw a circle. Then I try to connect them together by using a vertical line. This one is considered as our heat exchanger. Okay? Why I can pair up this one, stream number 1 with stream number 4? Because the CP of stream number 1 is lower than the CP of stream number 4. Okay, so look at here. Beside that, for stream number 4, I want to increase the temperature to become 140 degrees Celsius. Because this one is cold stream. So that's why when I calculate the heat energy that I need to supply to the cold stream here, I need to calculate based on the 140 target temperature here, and here the cold temperature here, 80. So 140 minus 80, what is the value? 60. 60 multiplied with 4.5, try to press your calculator. 60 multiplied with 4.5. 270. So meaning that if let's say I want to increase the temperature from 80 degrees Celsius to become 140, I need to supply 270 kilowatts. Oh, fortunately, you see, the energy they release in the first process stream here is actually sufficient, can be transferred to the stream number 4 here. So meaning that I can increase the temperature of the stream number 4 here by using the heat energy released out from the first stream here. Remember, for hot stream, I minus the value based on this one value and also the hot stream pinch temperature here. For cold stream, I use the value here minus the pinch temperature of the cold stream here. So that's why I ask you to label hot and cold. So make sure you use the correct value to calculate. Okay, so meaning that later in your revised process flow diagram, later the stream number 1 and stream number 4, you will install a heat exchanger. Okay, stream number 1 will be transferred into a heat exchanger. Stream number 4 will be transferred into the heat exchanger here in order to recover the heat energy. So in that case, you can reuse the heat energy here and remove the heater and cooler that actually you initially installed in the previous process flow diagram to reduce the cost that required to install the cooler and to reduce the cost of the utility and also increase and make your chemical plant become more eco-friendly. This is the meaning here. Okay? Okay, okay, so now I proceed. Okay, we proceed. Look at here. Okay, just now I pair up the stream number 1 with stream number 4. So now I have another hot process stream again. You see, okay, stream number 2. What is the CP? 1. Okay, cold stream number 3. What is the CP? 2. 1 smaller than 2. So means that if let's say I pair up 2 with 3, it can meet the regulation here. So that's why I install the second heat exchanger. This one is heat exchanger and link them together. Similar, what is the heat energy I can remove out from the hot stream here? 150 minus 90. The answer is 60. 60 multiplied with 1, 60 kilowatts. So that means the energy I can remove out from the hot stream number 2 here is 60 kilowatts. What is the energy that actually I need to supply to the cold stream number 3 here? 135 minus 80. 55. 55 multiplied with 2, 110 kilowatts. I need to increase the temperature. Sorry, I need to supply energy 110 kilowatts. Then only I can increase the temperature from 80 to become 135. But now what is the energy that actually is sufficient? What is the maximum energy that actually can be supplied by the stream number 2 here? 60 kilowatts. But never mind, even though the energy I can supply and recover from the hot stream here is actually lower than what I want. But never mind, I still can try to recover the energy, install the second heat exchanger. Then 100, okay, 110 minus the energy that already supplied 60. What is the balance? 50 kilowatts. So the remaining 50 kilowatts energy that I require, I can install a heater here. Okay, I think this one, the symbol is wrong. Should be this one, okay? Okay. Okay, so that means, okay, 110 minus 60, the balance is 50. So that means another balance 50, I can install a heater in order to supply the balance 50 kilowatts that require. So in that case, for the total energy that require here, part will be recover and reuse the energy that reaches out from the hot stream number 2 here. And the balance, even though it is insufficient, but I can install a heater in order to achieve the target temperature that I want. So meaning that after I install the heat exchanger, after I recover and reuse the energy that require, now the new hot utility that I need to supply to my chemical plant is 50 kilowatts. And you see the 50 kilowatts, the value here is actually similar to the minimum hot utility that you calculate in the cascade diagram here. So meaning that based on the heat exchanger network that you design, the new fresh hot utility that you are going to supply to a chemical plant, this value is actually the minimum, the lowest value that actually you can achieve in your chemical plant. So meaning that you already can be considered fully optimized and reduce the fresh hot utility that require in your chemical plant. Okay, so meaning that here we have 2 heat exchanger you are going to install in order to recover the heat energy. Okay, so far any question before we move on to the right hand side? No, okay. Remember, okay, when you install the heat exchanger, right? Left hand side, you can only pair up the hot stream on the left hand side with the cold stream on the left hand side. You cannot cross the pinch point. Pinch point here is actually considered as a boundary. So that's why this is the reason why we need to determine the pinch point in order to separate the design here into 2 different regions. The heat exchanger, the heat recovery cannot cross the pinch point here, remember. Okay, so now we proceed last part. Okay, now just now we focus on left hand side. Now we go to the right hand side. Okay, so now we go to the right hand side. Just now the left hand side we have a criteria we want to meet. So for right hand side, just now left hand side we also have criteria. For right hand side we also have criteria. But now you see for right hand side, now the new criteria that we want to meet is the CP of the hot stream must be bigger or equal to the CP of the cold stream. So that means later when you want to pair up the hot stream with the cold stream, you want to install a heat exchanger, you need to make sure their CP meet the criteria here. Okay? Okay. So similar. Okay, look at here. Okay, you see stream number 1 here. What is the CP here? 3. What is the CP of the third cold stream here? 2. Bigger? Yes, bigger. What is the CP of the last process stream here? 4.5. Bigger? Yes, CP of stream number 1 bigger than the CP of stream number 4. So that means now we have an option. Either we pair up the stream number 1 with stream number 3 or 4. Okay, but you look at here, what is the initial temperature of the stream number 4 at T? What is the pinch temperature of our cold stream at T? At T minus at T, 0. That means no temperature changes involved in this part. So meaning that no energy is required to supply to the stream number 4 here. So if let's say you proceed to minus 80 minus 80, 0. 0 multiplied with 4.5, the heat balance for stream number 4 on the right hand side is actually equal to 0, meaning that no energy is actually required to proceed to supply to the stream number 4 on the right hand side here. So meaning that in this case, what we need to do is we just proceed to pair out the stream number 1 here with stream number 3 here. So we can ignore stream number 4. This is how we make the decision for the pair. Okay? Okay, so look at here. So now we proceed, okay, we draw the heat exchanger and link them together. Okay? Okay, so next, okay, I need to know what is the amount, okay, of energy that actually I can transfer and supply to the cold stream number 3 here. How to calculate? We use hot pinch temperature 90 minus 60. Why? Because this one is hot stream. 90 minus 60, 30. 30 multiplied with 33, with 3, 90. 90 kilowatts. So I can supply 90 kilowatts to the third stream here. But I need to check what is the heat balance that actually I need to supply to stream number 3 here. How to calculate? 80 minus 20, 60. 60 multiplied with 2, 120. Okay, 120, okay, you see, what is the amount that actually I can supply? 90. So here, I supply 90 kilowatts. So at least, okay, from the payout here, actually I already fully recover and reuse all the energy that released out from the process stream here and supply to the third process stream here. Even though the energy I supply is actually insufficient, but never mind. Okay, at least we try to reduce. Okay, so 120 minus 20, 120 minus 90, what is the balance of the energy that I need to supply? 30. Okay, where is this 30 kilowatts I can supply? Where is this 30 kilowatts actually I can supply to a process stream here? From the second process stream here. Okay, you see, this one is hot stream. Hot stream 90 minus 30, 60. 60 multiplied with 1, 60. So that means maximum I can supply up to 60 kilowatts by using the second process stream here. But now I only need supply 30 kilowatts. So that's why never mind, I still install the fourth heat exchanger and try to transfer 30 kilowatts to the cold stream number 3 here. 60, I already supplied 30 to stream number 3. So what is the balance? 30 kilowatts. So meaning that the remaining 30 kilowatts in the hot stream here, I can try to remove it by installing a cooler. The cooler will assist me to try to remove the remaining 30 kilowatts in order to make sure the hot stream or stream number 2 can reduce its temperature to achieve 30 degrees Celsius here. Okay, so by doing this way, I can try to supply all the energy that required by the cold stream here and also reduce the energy that I need to supply to the stream number 2 here in order to make sure it can achieve its final temperature. And you see, by installing another 2 heat exchanger, now the fresh, okay, cold utility that I need to supply to my chemical plant is actually reduced to become 30 kilowatts. And this value is actually similar to the minimum value that actually I can achieve in my chemical plant design here based on the cascade diagram, 30 kilowatts. The 30 kilowatts that show in the cascade diagram is actually the minimum value that actually you can achieve. If let's say you try to develop a correct, okay, or a proper heat exchanger network, then you can actually achieve the minimum fresh coal utility that you need to supply to the chemical plant. So you see, the value is similar, 30. This is how we develop the network design, okay, heat exchanger network design or heat exchanger network, okay. Okay, so look at here. Okay, I remove all my drawing. I need to explain something. Okay, you see. Sir, just now you told me for right hand side, if let's say I want to pair up the hot stream with cold stream, I need to meet the regulation here. Whoa. So this one okay lor, okay? You see the specific the heat capacity of hot stream number 13 is bigger than this one too. So this one all can be accepted. Okay, now you look at this one. You pair up the stream number 2 with stream number 3 by installing this heat exchanger here. But you see, if let's say you compare the CP of stream number 2 is actually smaller than the CP of stream number 3. It cannot meet the criteria here. But why we can do so? Why we are allowed to install this heat exchanger? Okay, this one, why? Okay, so just now, okay, let's say for this one heat exchanger, we need to follow this one, the regulation or criteria here. Why? Because the temperature okay, let me think, okay, how to explain, Okay, let me think how to explain this one. Okay, so if let's say initially we don't have this heat exchanger, the intention we want to install the heat exchanger because we are trying to make sure the process stream here we can bring out its temperature to directly to achieve the pinch temperature of the cold stream here at 80 degrees Celsius. So that's why when we initially install this heat exchanger, we need to make sure, okay, we meet the criteria here. Okay, but okay, after we try to install this heat exchanger, because the heat energy that can be supplied in the first process stream here is actually insufficient, we cannot directly to bring out the temperature directly to 80 degrees Celsius. Okay, in that case, maybe we can just only bring out the temperature to become, let's say, 70 or maybe 60, which is lower than the 80 degrees Celsius. So in that case, okay, what we need to do is we can actually top up the balance, the energy that require of our stream number 3 here by using the hot stream number 2 here. So meaning that we recover the heat energy from the process stream number 2 here in order to top up the balance, the remaining of the heat energy that required by stream number 3 here. So in that case, because you see, we try to install the heat exchanger here. And some more the heat exchanger here, okay, it cannot directly, because only 30 degree kilowatts only, it cannot directly to increase the temperature of the cold stream here to achieve the pinch temperature that we want. So in that case, this one, the heat exchanger here, even though the CP, the pair out here cannot meet the criteria, but we are allowed to do so. This is considered as an exception. Why? Because if let's say you install this one, then only you found the energy is actually insufficient. Then only you proceed to install a heat exchanger here. So maybe the heat exchanger here can bring out the temperature from 20 to become, let's say, 35 degrees Celsius. Then later, the energy that provided by the third heat exchanger will further to bring out the temperature from 35 to become the temperature 80 degrees Celsius that you want. So in this case, because the heat exchanger here, it didn't directly bring out the temperature, initial temperature, directly to the pinch temperature of the cold stream that you want to achieve here. So that's why for this heat exchanger, it can be excluded, and the criteria here, the heat exchanger here, it can actually given an exemption and no need to follow up the criteria here for the heat exchanger here. Why? Because it cannot directly bring out the temperature directly to achieve the pinch temperature here. Okay, but if let's say we only install the heat exchanger here, we don't have this exchanger, we don't have this heat exchanger, and some more the energy that we're going to supply can directly increase the temperature from 20 to achieve the pinch temperature of the cold stream that we want to achieve here, then yes, then we need to make sure the criteria of the heat exchanger here must fulfill the criteria that given here. So that's why in this case, for the number 4, the heat exchanger number 4 here is given an exemption. Okay, so far any question? Okay, no, okay, so be careful, this one is actually, even though the heat exchanger here, it cannot meet the criteria, but okay, it still can be accepted. Why? Because okay, the energy that's supplied by the heat exchanger number 4 here, okay, it cannot directly to bring the initial temperature to the pinch temperature. So that's why, okay, excuse can be given and no need to follow the criteria here. So that's why, okay, if let's say you try to combine the left hand side and right hand side together, then total how many heat exchanger that actually you can try to install in your chemical plant? Total there are 4 heat exchanger you can install in your chemical plant. You see, 1, 2, 3, 4. There are 4 heat exchanger. Then in this case, based on all the process stream that involve, you only need to install a heater and also a cooler. And some more the hot stream or hot water, the energy that need to supply is only 50 kilowatts. And this is the minimum value that actually you can achieve in your chemical plant. And also for the cooler, the cooling water, the minimum full utility, 30 kilowatts, okay, you need to supply to your chemical plant. Okay, this is how we develop and design heat exchanger network. And this is actually the final solution based on the pinch analysis. And this is how we determine the number of heat exchanger that we need to install in the chemical plant. And all and what I explained just now, already cover the content, they are written and given in the lecture notes here. And actually the step, how we carry out the pinch analysis and draw the heat exchanger network, is similar to the heuristic that given here.